For billions of years, no eye, human or machine, had ever seen this. Now, for the first time, we've captured it. A place of fire, silence, and secrets. The South Pole of the Sun. We see it every day. It rises in the east, sets in the west, and warms our world with its constant light. But in truth, the Sun is a wild, complex engine of fire, magnetism, and mystery. From Earth's perspective, we always see the Sun from roughly the same angle. We're stuck in the plane of the solar system, what scientists call the So even our most advanced solar observatories, like the Solar and Heliospheric Observatory or the Solar Dynamics Observatory, could only view the Sun's equator and the Sun's 11-year activity, cycle the rise and fall of sun flares and energy bursts is driven by processes deep inside the Sun and influenced by what's happening at its poles. To leave the flat plane of the solar system and tilt upward toward the Sun's hidden ends. That dream took shape in a joint mission between NASA and the European Space Agency. They called it Solar Orbiter. For the first time, it tilted far enough to capture detailed images of the Sun's south pole. What came back wasn't just a scientific milestone, it was a moment of quiet awe. Each time the cycle shifts, the magnetic field actually flips, switching north and south. But we had never directly observed the poles during this crucial time. We could watch how the magnetic field curved and twisted near the pole, how it might influence the entire 11-year cycle. It was like seeing the gears inside a clock. We've always heard ticking but never opened. That magnetic energy shapes the heliosphere, a bubble around our entire solar system created by the solar wind. Thanks to Solar Orbiter, we can finally see it. And this is just the beginning. Over the next few years, as the spacecraft tilts even farther out of the ecliptic, its view will improve. We'll get better images, clearer patterns, and hopefully answers to questions that have puzzled solar scientists for generations. The South Pole, then, isn't just a feature of the Sun, it's a gateway. There's a quiet thrill in seeing something no one has ever seen before, a piece of the Sun, hidden from us for all of human history, now laid bare. And it's beautiful, not because it's dramatic or dangerous, but because it reminds us how much is still out there, waiting to be discovered even in places we thought we already knew. A place where solar energy leaves the star and begins its journey across billions of miles of space, not just closer than ever before, but from above and below the solar equator. This would allow it to peek at the pole, something no spacecraft had ever done. But to get that view, the spacecraft needed time. Swirls of magnetic activity, strange filaments, subtle differences in brightness and texture. It looked both familiar and alien, not chaotic, but not peaceful either. There's no surface, no ice, no land, just plasma superheated, charged, gas moving in vast, dynamic patterns. The temperature near the surface can reach 5,500 degrees Celsius, while the outer atmosphere, the corona, can soar to over 1,000,000 degrees. Why? That's still one of the Sun's great mysteries. But the poles may hold part of the answer, like watching a thunderstorm from space, silent, beautiful, and full of power. Years, in fact, to gradually adjust its orbit using the gravity of Venus, each time climbing a little higher above the Sun's equator. We were guessing based on patterns, simulations, and indirect data. The poles, always out of reach, and until recently, a part of it had never been seen by any human or machine, its South Pole. These observations could help predict solar storms, those powerful bursts of radiation that sometimes knock out satellites or disrupt power grids on Earth. 1. The hidden pole of a familiar star. That's the situation scientists faced for decades. We could see the Sun's storms, we could measure solar cycles, but without seeing the poles, we were missing a huge part of the puzzle. Think about that. We've sent probes to the edges of the solar system. We've mapped distant galaxies, but we never looked directly at the Sun's South Pole until now. They play a central role in how the Sun behaves. The Sun isn't just a glowing ball. It's a magnetically active sphere, constantly shifting and pulsing with cycles of energy. Sunspots, solar flares, and even the solar wind, all these are tied to the Sun's magnetic field. And where does that magnetic field begin and end? At the poles. Let's begin with something so close, so familiar, that we often forget how little we truly know about it, the sun. That's right. For all our satellites, telescopes, and space missions, the bottom half of our closest star remained a mystery. Why is that? The answer is surprisingly simple. Position. But the poles aren't just another part of the sun. Imagine trying to understand how a planet spins without ever seeing its axis. This blind spot mattered. So for years, space agencies dreamed of a way to see what had never been seen. Launched in early 2020, Solar Orbiter was built with one bold goal: to study the sun from new angles. And in June 2025, after 5 years in space, Solar Orbiter finally reached the right position. The first images showed patterns never seen before. But beyond the beauty, scientists saw clues. Clues about how sunspots form, how magnetic fields evolve, and how energy flows from the poles into the solar wind. For the first time, we had a direct line of sight into one of the most important engines of solar behavior. What makes this even more incredible is that the south pole of the sun is nothing like the south pole of Earth. Scientists believe the polar regions are where much of the sun's magnetic field gets reorganized and pushed outward into space. Until now, we've only guessed what this gateway looks like. But beyond all the data, there's something deeper. Chapter 2. The journey of Solar Orbiter. Getting a glimpse of the sun's south pole wasn't easy. In fact, it took decades of planning, collaboration between continents, and a spacecraft unlike anything sent before. To truly understand why this moment matters, we need to go back not just to 2025, but to the origin of the mission itself. The story of Solar Orbiter begins in the early 2000s, when scientists realized they needed a better view of the sun's entire surface, not just from the front, not just the equator, but from the sides, from above, and from below. It carried 10 scientific instruments, each designed to capture different aspects of the sun's activity: ultraviolet imaging, magnetic field readings, solar wind data, and more, to gradually leave the flat plane of the solar system and look at the sun from a steep angle. But here's the challenge. Physics doesn't make that easy. They imagined a probe that could move close to the sun, survive intense heat, and tilt its orbit to gain a unique perspective. By June 2025, it had reached an angle high enough to give scientists their first real look at the sun's south pole. But building that kind of spacecraft would be expensive and complex. The temperatures are brutal. At its closest point, Solar Orbiter travels just 42 million kilometers from the sun, closer than Mercury. To survive, the spacecraft was equipped with a custom-built heat shield made of titanium and coated with a special material called solar blast. This shield keeps the instruments cool while the sun blazes just outside. At the same time, other instruments measured the solar wind, the magnetic fields, and the patterns of charged particles escaping into space. To make it happen, ESA teamed up with NASA, forming one of the most ambitious solar missions in decades. To capture detailed images of the South Pole, Solar Orbiter had to align its high-resolution cameras with the correct angle, sometimes within just a few arc flares, and eruptions reaches its peak. It's the image of this small spacecraft, millions of kilometers from Earth, quietly turning its lens towards something we've never seen. The sun has watched over us for our entire existence. It powers every plant, every ocean current, every heartbeat, and yet it still holds secret corners we've never explored, angles we've never viewed. With Solar Orbiter, we've finally taken a step toward filling in that blind spot. All those years of planning, all those calculations, just to get a better look at something we thought we already knew. Capturing polar data during this active phase offers insights we've never had before. That's like aiming a camera at a coin from 100 kilometers away. By the early 2030s, it could reach an inclination of 33 degrees, giving us even clearer views of both poles. The polar regions are like the control centers for solar magnetism. By observing how energy flows there, scientists can better model the sun's behavior and maybe even predict its storms. And because the spacecraft is constantly spinning and adjusting its orientation, maintaining that level of focus is incredibly hard, and along the way, it's likely to raise new questions. That's how exploration works. Each answer opens a door to something else. Not just as a theory, not as a simulation, but as it is real, dynamic, and alive. They needed a way to see the poles, measure magnetic fields from a new angle, and track how energy flowed across the entire star. No existing spacecraft could do that, so the European Space Agency, ESA, started designing something new. They called it Solar Orbiter. What triggers massive solar eruptions that can disrupt satellites and power systems on Earth? Launched on February 10, 2020. From Cape Canaveral, Florida, Solar Orbiter wasn't just heading toward the sun, it was heading into uncharted territory, one of the most critical goals. Most planets and spacecraft orbit in the same flat disc-shaped plane, known as the It's like being stuck on a dinner plate. If you want to rise above the edge of that plate, you need a huge amount of energy, and that kind of energy isn't practical for a single rocket. Instead, Solar Orbiter took a slower, smarter route. It used gravity. Over the course of several years, the spacecraft performed a series of gravity assist maneuvers, flybids, of Venus, designed to adjust its path bit by bit. Each time it passed the planet, it borrowed a little of Venus's orbital energy, changing its trajectory without using fuel. It was like using the planet as a cosmic slingshot. This technique takes time. Between 2020 and 2025, Solar Orbiter made multiple flybys, each one lifting its orbit just a little higher. But navigating so close to the sun brings other challenges. The spacecraft also had to be extremely precise, but it worked. During its closest pass in June 2025, Solar Orbiter used its extreme ultraviolet imager to snap the first detailed images of the Sun's south pole. For the first time, scientists had a three-dimensional view of the Sun's activity from pole to pole, and it wasn't just about pictures. These measurements help answer long-standing questions. Why do sunspots appear in cycles? How does the magnetic field reverse every 11 years? The answers lie not just on the surface of the Sun, but deep within its structure. The timing was perfect. The Sun is currently ramping up to its next solar maximum, expected around 2025 to 2026. That's when solar activity. But perhaps what's most powerful isn't just the science. There's something poetic about it, and this is just the beginning. Solar Orbiter will continue making flybys of Venus, lifting its orbit higher each time. Each pass will offer more data, sharper images, and deeper understanding. But for now, what matters is this. We've seen the south pole of the Sun. Chapter 3. What the images revealed. When the first detailed images of the Sun's south pole arrived from Solar Orbiter, scientists paused. For years, they had relied on computer models and indirect data to imagine what this region might look like. Now, for the first time, they could see it with their own eyes. The view was breathtaking, familiar, but at the same time, strange. The instruments on Solar Orbiter revealed patterns of magnetic field lines bending and twisting around the pole. Some of these lines connected directly to the open regions of the corona, which are responsible for the high-speed streams of solar wind that can reach Earth. These tiny bursts of energy, far smaller than traditional solar flares, may help explain why the Sun's outer atmosphere, the corona, is so much hotter than its surface. The surface temperature of the Sun is around 5,500 degrees Celsius, but the corona can exceed 1,000,000 degrees. This mystery, known as the coronal heating problem, has puzzled astronomers for decades. The new images hint that countless small eruptions near the poles may contribute to heating the corona in ways we never understood before. For decades, scientists have known these polar winds play a role in shaping space with it, but until now, we could only guess how they form. The magnetic fields we see twisting around the pole are the same fields that create auroras, those glowing curtains of light in the night sky. It is a reminder that everything on Earth, from the tides to the seasons, depends on the moods of this distant, fiery sphere. The solar wind escaping from coronal holes eventually interacts with our planet's atmosphere, painting the sky with colors that have inspired humans for thousands of years. It wasn't just another step in solar research, it was a first glimpse into a region that has remained hidden for billions of years. Solar Orbiter will continue sending images over the next decade, each one sharper and more detailed than the last. As the spacecraft tilts even farther out of the Sun's equatorial plane, the view of the poles will become clearer. We'll see more of those filaments, more of the campfires, and perhaps discover phenomena we can't even imagine yet. A part of our closest star that no one had ever seen. because while the sun's poles may seem distant and abstract, their influence is real. From space, whether to satellite safety, understanding the South Pole could change how we prepare for the future. These eruptions, known as coronal mass ejections, can have serious effects on Earth. Scientists used to think of the sun's poles as relatively calm compared to the equator, where sunspots and flares are more frequent. But the images from June 2025 suggest that the poles are just as dynamically in different ways. Instead of large sunspots, the poles seem to be filled with smaller, more subtle structures that continuously shape the sun's magnetic landscape. When directed toward our planet, they can disrupt power grids, knock out satellites, and even affect aviation and communications systems. This difference in rotation, called differential rotation, is one of the drivers of the solar cycle. By observing the pole directly, scientists can measure this rotation with unprecedented accuracy, refining our models of how the sun's magnetic field evolves over time. By studying these polar regions, we may gain the ability to predict such events earlier and protect our technology from sudden disruptions. The images gave us the first clues. The surface appeared as a restless sea of plasma, twisting and folding in complex patterns. There were regions of bright, glowing loops and darker patches that stood out like holes burned through a sheet of light. Looking at the South Pole, you can't help but feel small. This glowing, turbulent star, 150 million kilometers away, is the source of every drop of energy that reaches Earth. And yet, for all our technology, we're only now beginning to understand its most hidden corners. These are called coronal holes, and they're among the most significant features revealed by the new images. From these dark zones, streams of charged particles escape into space, becoming part of the solar wind that flows through our solar system. Over time, this field becomes twisted and tangled. Every 11 years, it flips north becomes south, and south becomes north. This flip drives the cycle of solar activity, which affects everything from satellite communication to auroras. By seeing the pole directly, scientists can now watch the very region where much of this cycle begins. The images also showed filaments, long, thread-like structures of plasma suspended above the surface by magnetic fields. These filaments were larger and more intricate near the pole than expected, hinting at magnetic activity that differs from what we observe closer to the sun's equator. Each of these structures is a reminder of the sun's power, vast rivers of energy moving through a star that is 109 times wider than our planet. But the real surprise wasn't just in the visual beauty, it was in the magnetic data. Think of the sun as a giant, turbulent dynamo. Its magnetic field is generated by the movement of charged particles deep within its interior. Another fascinating discovery was the small-scale magnetic patterns, nicknamed solar campfires. The South Pole also displayed signs of polar crown, filament structures that can erupt and send massive clouds of solar material into space. What's remarkable about the new data is how much it challenges previous assumptions. The pictures also revealed that the South Pole rotates slightly differently than the equator. But beyond all the science, there is a sense of wonder. The images from Solar Orbiter aren't just data points. They are windows into a living system, one that has shaped life on Earth since the beginning. In a way, looking at the South Pole of the Sun is like looking at the source of all these wonders. This is why the release of these images caused such excitement among scientists and space enthusiasts alike. And the best part, this is just the beginning. In the next chapter, we'll take a closer look at what these discoveries mean for Earth. Chapter 4. What the solar South Pole might be telling us. If you've ever watched the northern lights shimmer across the sky, you've seen firsthand how connected we are to the sun. Those glowing waves of color are caused by solar energy interacting with Earth's magnetic field. But here is something fascinating. Much of that energy comes from areas near the sun, exposed regions we've barely understood until now. So when the Solar Orbiter gave us our first real look at the sun's South Pole, scientists around the world leaned in, not just because it's new territory, but because what we find there could reshape how we understand space weather and its impact on Earth. Think of it like a stream of energy flowing out from the pole, rising up into space in thin, bright lines. If we can understand the rhythms and signals coming from the poles, we might one day predict solar storms with more accuracy. That could give us time to protect satellites, reroute flights, or safeguard astronauts in orbit. These solar plumes aren't well understood, but they might help guide solar wind, a steady stream of charged particles the sun sends out in all directions. When aimed at Earth, solar wind can compress our planet's magnetic field and create stunning auroras. It's sending out signs, sometimes quiet, sometimes dramatic, because space weather isn't science fiction, it's tomorrow's forecast. And now, for the first time, we're finally seeing where some of those signs begin. But too much solar wind, or an especially fast one, can overload power grids and communication systems. One solar flare can disrupt everything from internet service to stock market trades. And yet, by studying the poles, we're learning how to ride the waves of that energy instead of being caught off guard. Let's talk about sunspots. They might sound simple, but they're a big deal. These dark patches on the surface of the sun are cooler than the surrounding areas, and they often mark places where intense magnetic activity is brewing. Some researchers are exploring whether the polar regions hold clues about solar grand minima, periods when sunspots vanish almost entirely and solar activity drops dramatically. It's like opening a book written in a language we're just beginning to decode. The swirls, dark spots, and bright plumes, their messages from our star, and slowly, patiently, we're learning to read them. The last time that happened was during the Maunder Minimum in the 1600s, a period that coincided with a mini ice age on Earth. Could changes in the solar poles be an early warning of another shift like that? That magnetic energy can build up and suddenly explode, sending powerful solar flares or coronal mass ejections, EMEs, hurtling into space. If one of those hits Earth, it can knock out satellites, mess with GPS, or even cause blackouts. So keeping an eye on where sunspots form and how they behave is crucial. Now, here's the catch. Sunspots don't just pop up randomly. They follow a pattern, one that's closely tied to the sun's 11-year activity cycle. We were peering into the possible source of powerful solar storms. The images showed swirling magnetic fields and darker patches. That might be early indicators of the next sunspot cycle. It's a little like seeing the first cracks in a dam before the flood. Subtle, but deeply important. Every cycle, the sun's magnetic field flips north, becomes south, and vice versa. And during this cycle, sunspots tend to drift toward the equator. But where do they start? That's where the poles come in. Scientists believe the polar regions may act like incubators, storing magnetic energy, building up pressure, and eventually releasing it as sunspot activity closer to the sun's midsection. So when we finally got a clear view of the sun's south pole, we weren't just looking at a quiet, icy landscape. Another intriguing feature observed was something called the plume structure. This is why the South Pole matters. It's not just about curiosity, it's about preparation. What makes all of this even more compelling is the sun's long-term behavior. We don't have all the answers yet, but each new image from the South Pole brings us a step closer. It's also a humbling reminder. For all our technology and progress, we're still passengers orbiting a massive, volatile ball of energy. So the next time you look up at the night sky, remember, the sun isn't just shining down on us. In the next chapter, we'll explore how these discoveries might change the way we live and work here on Earth. Chapter 5. The Future After the First Glimpse. Now that we've seen the sun's south pole for the first time, the big question is, what happens next? What do we do with this knowledge, and how could it change the way we live, plan, and protect our world? The simple answer is this: seeing the sun from new angles helps us predict the unpredictable. Just like weather forecasting changed forever once we started observing Earth from orbit, space weather forecasting is about to take a leap forward, but these delicate machines float in an environment that's anything but gentle. A strong solar flare can fry electronics, corrupt data, or send satellites tumbling off course. By watching the sun's polar regions more closely, we can detect early signs of an upcoming storm, maybe even days or weeks in advance. And until now, we've only been seeing half the picture. That's enough time to switch satellites into safe mode, move astronauts into shielded areas, or reroute long-haul flights away from polar routes, where solar radiation is most intense. For centuries, humanity has stared at the sky, trying to understand the stars. We built telescopes, launched probes, and sent rovers to Mars. But all along, the biggest mystery has been right in front of us: the sun, the star that makes life on Earth possible. We've stared at its face, tracked its flares, and studied its corona during eclipses. We've started decoding the sun's rhythms, its cycles, its moods. We've peeked behind the curtain into a region of space no one had ever seen before. And what we find there: swirling magnetic fields, glowing plumes, mysterious dark regions will guide the next generation of discovery. And yet, the poles remained invisible, untouchable, unknown. We dive into the mysteries that shape our universe quietly, slowly, and with wonder. Hit the bell so you don't miss the next story, because sometimes the biggest questions are still hiding right in front of us. For the first time, we read not just guessing what the sun might do next, we're starting to understand why it does it. The sun gives us light, warmth, and life, but it also reminds us how fragile our technology is. A reminder that exploration isn't just about finding new places, it's about finding new perspectives. And sometimes, all it takes is looking at something familiar from a different angle. How delicate our modern systems are, and how much more we still have to learn. Let's look at one practical example. Satellites. We depend on them for navigation, communication, weather, defense, and even banking. NASA and the European Space Agency are already discussing future missions that could orbit the sun even more closely or hover over the poles for extended periods. New telescopes on Earth and in space will use the data we've gathered to build more accurate models. Artificial intelligence will sift through mountains of solar data, spotting patterns no human could see. And slowly, we'll start to treat the sun not just as a ball of fire in the sky, but as a dynamic, complex system that shapes everything we do. But the implications go even further. Some scientists are starting to wonder whether changes in solar activities, especially at the poles, might connect to deep shifts in Earth's own systems. Historical records showed that long periods of low solar activity sometimes align with cooler temperatures on Earth. Like during the Little Ice Age, could the south pole of the sun hold clues not just about solar storms but about our planet's climate future? Many research future of the sun decades, or even centuries ahead. Some models suggest that fluctuations at the poles can predict whether the next solar cycle will be mild or extreme. That matters more than you might think. A hyperactive sun could overwhelm Earth's magnetic field and increase radiation exposure for airline crews, astronauts, and even passengers on high-altitude flights. A quieter sun, on the other hand, might reduce these risks but could also affect Earth's climate in subtle, long-term ways. And here's where things get a little strange. We're not saying the sun is the only factor in climate, but it is certainly one of the biggest. There's also something deeply symbolic about this first glimpse of the solar South Pole. Now that's changing. And it's not just solar orbiter. But let's pause for a moment and think about what this really means. We live in a time when humanity is beginning to understand the forces that have shaped our world for billions of years. So what's next? More missions, more data, better predictions, but also a deeper awareness that we're part of a much bigger story. In a way, this first glimpse of the solar South Pole is more than a scientific milestone. It's a turning point. Because sometimes the secrets we've been searching for are right there, hiding in plain sight, at the edge of the light. If this journey into the unknown corners of our own sun sparked your curiosity, consider subscribing.